Okay, so today we're going to start by discussing more advanced decision tree methods, starting with regularization. And regularization is the rough idea that we're going to apply Occam's razor. So all else being equal, we want a smaller model. And so we're going to see a variety of ways of creating smaller models that have the same performance. So let's start off by using the universal bank data set. So we're going to set the working directory, then we're going to load up tidyverse and caret. Remember that caret stands for classification and regression trees. We read in the data set into a data frame, and then we take a look at it. It's the same as yesterday, obviously. So we're going to do the same manipulations that we did yesterday. It's always good to run some summary statistics and then to look at the structure. And so we're going to drop the ID and zip code as we did before. We have to run it correctly. Okay, and then we're also going to create factors out of personal, loan, and education using these levels, right? No and yes for 0 and 1, and then for 1, 2, and 3, undergrad, graduate, and prof. Okay, and then we just have to click it correctly so that it shows up. Okay, good. Okay. All right, so now we're going to split the training and testing set using create data partition. Okay, so create data partition, we're going to split it 60%, and we'll do the same check that we did yesterday. All of this code we've already seen before. So let's just look at the dimensions. So we look at bank, which is 5,000, then train DF, which is 3,000, then hold out DF, which is 2,000. Okay, now we're going to try to avoid overfitting, and we're going to see a bunch of variety of methods, right? So these are all regularization methods, which are going to end up with giving us a smaller tree, ideally that has the same or better generalization performance on the holdout data set. So the first idea is that we're going to do a grid search around the complexity parameter. So the complexity parameter basically controls the size of the tree, okay? And what we're going to do is we're going to check a whole bunch of parameters, settings for this parameter, and choose the best one. So we'll set our random seed, and now we're going to do cross-validation. Okay, so what cross-validation does in this case, since cross-validation is equal to 5, is it divides the data set into 5 parts, and then trains on 4 of them, and then runs on the 5th one. And it does that 5 times, one for each time. Okay, so this does a better job of giving us good accuracy than doing it a single time. Okay, and then the other thing we're going to do is that we're going to check these 5 CP values. Okay, so this is the tune grid parameter, and what we're going to do is we're going to do a grid search across all of them, right? So we're going to set C equals 1, and then we're going to do this 5-fold cross validation, and then C equals 0.1, and do 5-fold cross validation, and so forth. And then we'll end up with a table for each complexity parameter, what the performance was. Okay, so here's the result. So here, down here, we have the complexity parameter, so 0.001. Here was the accuracy. We'll primarily care about accuracy here. And as you can see, that for the first 4 levels, it was approximately the same, but then in the last one, it really falls off. Okay? So we're going to pick some parameter up in here. And in this particular case, the rough intuition here is that you want to pick something that is good and is sort of in the middle of everything, right? So we're going to pick like 0.001. If you pick 0.00001, that would be fine too, right? Here, they're actually not that big of a difference, okay? So then we're going to do a finer grain search around 0.001, right? So like 0.001, 0.002, 0.005, etc., and see if we can get something that's better. And so here we see our model results again, and here actually they're all essentially identical except for this last 0.005. But even this, it's 97.5 versus 97.6, okay? But the rough idea is the same, right? Which is you do a broad grid search, a coarse grain search, and then do a finer grain search across smaller and smaller numbers. And so you get a really good idea of what the parameters should be. Okay, so that is the first technique, okay? The second technique that we're going to learn about is stopping the tree growth, okay? So we'll see how to do that. Okay, so here we're having a min split of 5, so we're only splitting if we have at least 5 items in the node, okay? 5 items in the node. And then we're doing a cross-validation of 5. So let's run this, okay? And so what this shows now is for various depths of the tree, 1, 2, 3, 4, 5, 6, 7, all the way down to 11, and various complexity parameters, what the relative error is, okay? And so what we want to do now is we want to find the smallest X error and then go ahead and prune the original tree. So we find the minimum, okay? So this is the minimum X error, so we just find the minimum number on this. So that's 16, 13, 19. And then we're going to prune with this complexity parameter, 0.0002, okay? So here we go. And so this is that tree, okay? This is that tree, right? And then we can do something similar, except this time we use the lower CP with a 1 standard deviation as the cutoff, okay? So that's just standard statistical technique, okay? So here we're going to find the smallest one. This is the minimum error row. We'll just look at what it is. So let's just type in, oops. We type in, let's see what it is. Okay, so you see it's the 0.002. It's this one that we had discussed before. Okay, so we're going to take that one. Okay, and then we're going to add this minimum error standard deviation. Okay, so that's this. So 0.02. Okay, so we use cutoff. So we can see, let's just go ahead and run that. So you can see the result. Okay, so we've added those two things together, okay? And then we get this result, okay? That's the result we get. So min error row X error plus min error X standard deviation, okay? We get this X error. And so that should be, pretty straightforward to calculate. If you add X error to X standard deviation, you get this 0.18, okay? And then you run this cutoff, okay? And you get the best tree using that, okay? And now we're going to run it again. Okay, and we get obviously a much smaller tree because we've increased the complexity parameter, okay? And now what we do is we just start doing a bunch of comparisons, right? We can compare these trees to each other on the data sets, right? And so that's another way of getting it. Here are our classification rules, which we've seen before. You can always get them that way as well. And so those are 3 different ways to do regularization on classification trees. And now we are going to go ahead and look at regression trees.